Hey kids, guess what time it is? It's time for more math. And if you got your calculator, this is going to be good. Make sure that if you turn on your calculator, it's set to A plus BI mode next to real. It says A plus BI because we're going to be dealing with complex numbers again today. Some of this will be reviewed from both the video that we watched with Arthur Benjamin and our discussion over those, I don't know, was it 3 days of class when we were talking about complex numbers. So get your notes out. You're going to be writing some stuff today. And we're going to take a variety of applications for complex numbers, representations. Is my hat crooked? Hard to tell. Looks crooked, or my head's crooked. There's that better? Looks better. All right. Just remember, you never walk alone. I'm attaching on your stuff the reteaching for 69. You're going to be doing a little bit of graphing of complex numbers, and then on the back, some multiplication and division. Multiplying and dividing. All right, so that's what we're going to talk about today. How do we graph them? When we take powers of I, what happens? We'll look at that. The absolute value of a complex number, which sounds kind of weird. Yeah, powers of I, multiplying and dividing complex numbers. All good stuff. I think you'll enjoy this. A lot of it, the calculator will end up doing heavy lifting for you, but you should know how to do it on your own. First things first. That would be graphing complex numbers. I believe we talked about this before. That we said that a complex number of the form A plus BI is a two-dimensional number. That's different, isn't it? Two-dimensional number. And it is similar to graphing, if you're going to graph it, on the coordinate system, because the coordinate system point has two parts to it. Very similar to how a complex number has a real part and an imaginary part to go together, make one number with two parts. One number with two parts. That means it's two-dimensional. It has a dimension that goes along the real number line, and it has a dimension that goes along the imaginary number line. It's akin to x's and y's, but now we're going to say real, or the A part, and the imaginary, or the B part. The B there is actually just a scalar multiplier of a's. So I've drawn it kind of small, but if you're on a big screen, you can see it says 1i, 2i, 3i, 4i, and negative 1i, negative 2i, negative 3i, negative 4i. We're going to treat it just like an xy number, except it's an AB number. If it's an xy number, we're doing it on the coordinate or Cartesian plane. Thank you very much, Rene Descartes. If we're doing it a complex number, then we're doing it on either the polar or the complex plane, which is called the Argand plane. That's bonus material there. The complex plane has the real part going this way, and the imaginary part is on the vertical axis. So it makes graphing complex numbers pretty easy. If you just relate it to XY addresses, you'll understand how these things work. So I got 4 complex numbers here. And remember, 4 is still a complex number because its imaginary part is 0. And one that only has like 2i is 0 plus 2i, so it does have two parts. It's just one part is like along an axis. Same way that if we wrote the number 0, 4 in xy, it's not just the y part, it's on the x and then it's on the y. We just simplify it by writing the number 4 rather than the imaginary part, which is 0. Okay, so let's get to it. 2 plus 3i. 2 is the real part, so 2 out this way, 1, 2. And 3 is the imaginary part, 1, 2, 3. There's the point 2 plus 3i, right there. The point 4 plus 0i. 1, 2, 3, 4 plus 0i, it stays right there. There's our point 4, the complex plane. 0 plus 2i, 0 in the real direction, and then plus 2i in the imaginary direction. So there's our 0 plus 2i. And then the last one, 4 minus 2i, 1, 2, 3, 4 minus 2i. We end up right there. 4 minus 2i. So it's 1 point, right, with 2 parts. 2 parts of the address, just like xy, except now it's a and b. Pretty sweet, right? It could be in any 4 quadrants. It could be a negative 4 minus 4i if it's down here in 3rd quadrant. Same thing with cosines and sines and all that. We can relate the quadrant it is and the signs that they're associated with. So that's graphing complex numbers. You have to do some graphing on your reteaching. 3 minus I, 4i, and then a couple others where you graph it, and then you're going to find the next thing, which is the absolute value of a complex number. Let me clear this up here. I'll give myself another graph thingamabobber. And again, we'll have the real going this way, and the imaginary part, that axis going this way. Let's take the complex number 3 plus 4i. 1, 2, 3, 1, 2, 3, 4. Somewhere right there. 3 plus 4i. And now we want to know how far away is that point from the origin. What I'm going to do there is just I'm going to draw an arrow from the origin to that complex number. If we were doing this in math, in like physics, we call that a vector. Call it a vector. A vector has magnitude and direction, right? Magnitude and direction. If it's got magnitude, that's the length of the line, and direction tells you what angle it's at. Sounds like polar, doesn't it? We got a thing here, and then we're rotating it. Magnitude and direction. Vector. And we would like to know how long that vector is. Maybe it's forces. Maybe it's electrical current. No matter what it is. Yeah, so from the origin out to the point. And I guess a couple of things to say about this. Number one, the vectors always start at the origin and go to that imaginary number. And then number two, since we're measuring a distance rather than something else, the values for absolute values of complex numbers are always positive. We're always measuring the distance where we start to how far it is to where we end. Okay, always positive, always starts at the origin. And over here is the little formula for it. Complex numbers are often given the letter Z rather than an X or a Y or an A or a B. The absolute value signs there mean distance. Okay, so in complex land, when we say absolute value, we mean distance from origin. Hey! Okay, so it's the same thing as if we were doing right angle trigonometry. We're doing Pythagorean theorem, and Mr. McAndrews is getting itchy right now. Ouch. Don't bother the guy. Okay, so we're going to have the absolute value of this complex number, a plus bi, being, take the a part, the real part, square it, take the imaginary, whatchamacallit, it's not part, technically, it's the absolute values, scalar multiplier, whatever, the b part, and you're going to square that. Both these are going to have to be positive values because you're squaring things. Add them together, take the square root, there is your distance. So let's take our number over here, we do that with it, we'd say, what's the absolute value of 3 plus 4i? We're going to take a, which is 3, and square it. And we're going to add to that the 4, not the I, just the 4 part. We're going to square it. So we get the square root of 9 plus 16, which is the square root of 25, which is 5. Okay, so that says that vector right there is 5 units long. Does it look familiar? Because we're just counting up the 3 part and 4 part of a right triangle. So we're just using the Pythagorean theorem in a new and exciting way. It's a different application of that. We're saying, like, let's call it, I don't know what to call it. Let's get d for distance here. Distance squared equals the a part and the b part squared, and then we're just solving it. Ta-da! Pythagoras, all over again, in a brand new way. Super easy. I'm going to take one right off of your reteaching thing. This one's for free. So it's got graph each complex number and find its absolute value. They got the number 5 plus 2i. Okay, 1, 2, 3, 4, 5, 1, 2, it's over here. And we want to know how far is that from the origin 0, 0? We're going to take 5 squared and 2 squared, which equals 25 plus 4. That's a prime number. That's where you stop. You don't do anything else. You don't approximate it. You just say that must be the square root of 29. That's the correct answer. They even leave a little square root sign there for you to fill it in. I didn't use a calculator either. I like it when I don't have to use a calculator. It feels so good deep down inside. It's kind of like having a moment there with Mr. Rogers. All right, let me clear the board. I'll get back to you in like 2 seconds. Okay, let's do multiplication, and then we'll do powers of I, and then we'll do division, and then we'll be done. Talking fast here. Multiplication. You got one complex number multiplied by another complex number. You're going to do some FOILing. I believe that's on your algebra properties. Properties of complex numbers. It's got how we do that. Adding, subtracting, then multiplication. And it's got the little rule that's equal to AC minus BD. Just read the thing, Spence. Plus AD plus BC I. Okay, you're going to do the formula. You got AC, and then you got your ADI, and you got your BCI, and then you got your BDI squared. I squared is -1. That's where that comes from right there. They collected the real parts. They collected the imaginary parts so they can rewrite that number like a complex number. Now, that's a bunch of hoo-ha. Nobody ever sits there and says, oh, what's A and what's C, and they multiply and whatnot. They're just going to use the distributive property. Either this way, basically, where this gets multiplied by that and that, or FOILing. And everything will sort itself out. So if we do this, we've got like this complex number, 0 minus 4i, times this complex number, 7 plus 3i, we go negative 28i for that part, and this part is negative 12i squared, except that I squared is -1. So replace it. That makes this plus 12, and it's the real part, so it has to go first. And then this is the imaginary part, and it comes second. 12 minus 28i. And if I just typed it into my calculator like that and I hit enter, I get 12 minus 28i, which is, I'm smarter than the calculator. Well, I showed my work and the calculator didn't. Say that. The next one's just FOILing. So if we're going to follow the rules, we're going to go 5 times 6 is 30. 5 times -2i is -10i. We got plus 24i. That's nice. Those are going to go together. And then we've got this. We got minus 8i squared. I squared is -1. So I'm going to do that. That changes it to a plus 8. And we'll have 30 plus 8 for the real part. And -10i and 24i for the imaginary part. See how that's kind of set up like that one is? There. So this is 38. And this is plus 14i. I'm allowed to type that into my calculator too, just to check, of course. I wouldn't just do it on my calculator. Double check I got my signs right. See that I did it? Did you see that? And then there we go, 34 and 14, 38 and 14i. It's pretty nice, huh? Plus, especially since you can, double check your work on your calculator, that's pretty nice. Multiplication's pretty simple. The cool thing is when we see it on the grid and how multiplication rotates and expands things. That's where it gets fun. Okay, powers of I. That's our next topic. We're going to do a little thing called modular math now. Got like trigonometry was in there. We got some basic algebra, and now we're moving on to rotations and stuff. Powers of I. Clock math is what modular math is. So we're going to imagine we've got a clock, and it only has 4 places on it rather than 12. And these places represent remainders. Okay? This is what's called mod 4. It's got 4 places. And I can take any number, like let's take the number 17, and I'm going to divide it by the mod, by 4. And I'll get 4 remainder 1. Or I could start here and I could go forward 17 hours on this clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I end up over here at the 1. That's all I really care about is what's the remainder if I divide by what they call the modulus, the mod is. Okay? This is going to be the way that we're going to think about powers of I. If I've got, let's just start with 1. And I'm going to multiply it by I to the 1. I get I. And now I'm going to take I'm going to multiply it by I. I'm going to get I squared, which is negative 1. And then I'm going to take I squared times I, and I'm going to get negative 1I. If I take negative 1I, which is I cubed, right? I cubed times another I get I to the 4th, which is I squared times I squared, so that's negative 1 times negative 1, we get 1. And that's where we started. Start with 1 times I get I, times I get negative 1, times I get negative 1I, and times I get 1. If I was going to have that on the complex plane, I started right here at 1, I multiply by I get to here, where I get 1I. I multiply by I, and I get negative 1, which is right here, at negative 1. And then if I multiply by I again, I get right here at negative 1I. And if I multiply by I get back here at 1 again. So basically, multiplying by I equals 90-degree, and what do I say, anti-clockwise? Can I say that? "90-degree anti-clockwise rotation." It's pretty cool. But you can see that this is going to keep, this pattern is going to keep going. If I get back here and then I multiply by I again, I'm going to have this. And if I multiply by I, I'm going to be here. And I'm going to keep going around just the same way that I've got the clock, except I drew the clock the other direction. If we're going to take something like, well, let's take I to the 17th power. We don't have to sit there and go negative 1 times negative 1 times negative 1 times. No, all we got to do is divide that power by 4, take the remainder, and that's I to the whateverth power. Again, we just go around and around and around and around. 17 divided by 4 is 4 remainder 1. I'm going to take that remainder. I to the 17th power will give me the same answer as I to the 1 power. I. Try it on your calculator. Get your little I button there. I to the power of 17 equals I. So, yeah, any power. I got another one in the book. They say, how about to the 23rd power? Well, let's just take 3 and divide by 4. That would be what? 1, 2, 3, 4, 5 remainder 3. 5 remainder 3. We don't care about the 5 part. We just care about the remainder. Okay, so that's equal to I cubed. I to the 23rd power equals I cubed. 1, 2, 3, 4, 5, 6, 7, 8. Skip a few. 21, 22, 23. It's the same thing as I to the 3rd power. 1, 2, skip a few. Right, so if you've got lots and lots of big numbers of I, you can simplify that. It's going to have a remainder of 0, 1, 2, or 3. That's it. Once you hit I to the 4th, it's repeating itself all over again. I to the 4th is the same thing as 1. Lastly, let's do a little bit of division. Rocket. Alrighty, I'm going to start with not divisions, but I'm going to use this result in division, so hold on to your horses. Remember that Mr. Spence's favorite factoring form is the difference of two squares, where we would have, I'll do A's and B's. A plus B times A minus B equals A squared minus B squared, right? Difference of two squares. Okay, well, complex world has that extra little funny thing here. With the I, we know that if we multiplied those b's together, negative b squared, I squared, that the I squared part equals -1, and now we have plus b squared. So complex conjugates, you multiply a complex number by its conjugate. Remember, all we do is we change the sign in the middle. It's super cool because it's not the difference of two squares, it's the sum of two squares. A squared plus b squared equals a plus bi, a minus bi. So we can get around something like an x squared plus 4 now, which we couldn't do before. We just had to leave it there. But now we can say that the answers to that are x plus 2i and x minus 2i. Okay, so the beauty of it is if you've got a complex number, you can multiply by its complex conjugate and you won't have any more i's left over. This FOILed out will go x squared minus 2xi plus 2xi, so that part disappears, and then you get minus 4i squared. I squared is -1. -4 times a negative means positive. I have x squared plus 4. No complex parts of that expression anymore. They disappeared. Where'd they go? They went to imaginary land. Now, what's that have to do with the division? Complex numbers. Everything. Everything. Okay? It's like having my Joker moment here. Well, let's see. I'll leave that up there. All right, so let's take something less abstract because they've got an abstract thing here on the property of complex numbers for division. Don't even look at it. Let's take 3 plus 2i divided by 4 minus 2i. We want to clean this up. This is a problem because we basically have a square root in the denominator, and that's a big no-no. You're just not allowed to have those. It's not rational. You can't do lots of good math with it. So what we're going to do is what we did before, the same kind of situation. We're going to multiply the top and bottom by the conjugate of the denominator. But in complex world, this is an even easier problem because the bottom part resolves itself super duper easy. We already know what the pattern is. We already know that this complex conjugates are going to turn back into a squared plus b squared. There's a, there's b. 4 and 2. So the bottom resolves itself to 4 squared plus 2 squared. Every time. Every time. Square that number, add it to the square of that number, the a part and the b part, and you've got your denominator. 4 squared is 16, 2 squared is 4, denominator is 20. And what happens on the top? Distribution, FOILing. That's the hard part, it's the numerator. 3 and 4 is 12. 3 times 2i is 6i. 2i and 4 is 8i. And here comes the I squared part, plus 4i squared. I squared is -1. So that's real, and that's real. 12 minus 4 will give us 8, and 6i and 8i will give us 14i. The only thing is that we got to change that into a plus bi form, so we got to have 8/20ths plus 14/20ths I, or more simply, 1, 2, 2 divided by 4. Yeah, thank you. And 7/10ths. There we go. A plus bi form. Calculator can do division as well. Give yourself one of those fraction bars. Make sure everything's kind of like in parentheses, though I don't think you have to, but it's honest if you do that. 4 minus 2i was the original problem. 3 plus 2i over 4 minus 2i was the original problem, and lo and behold, it even gives it to me as a fraction. A plus bi form. Ain't that nice? You're welcome. You're welcome. So if you're asked on a test to show your work, you better. You're trusting your calculator that you typed things in, and remember, a lot of errors are user malfunctions. So I can't see a user malfunction when you take a test. I can't see that work, that you just pushed the wrong stupid button. But if you're showing me your work, you're showing me that you understand the concept, and there it is. There it is. We're using complex conjugates when we have division of complex numbers. This is really cool if you see it visually. Multiplying rotates it this way and expands things. Division rotates it back the other way and it shrinks things. It's pretty cool. We'll get to that later if you survive to pre-calculus, which I don't know. That's kind of pushing it, don't you think? All right, there you go. Calculator will do some of that heavy lifting for you. You should be able to complete the back portion of the multiplying or dividing. Calculator will help you out with some of that, except for number 8. Number 8, you're going to have to do it by hand because it involves some roots. But the rest of it, I've just laid on a platter for you. You're welcome.